Hello everyone. So welcome to IIT and Gate classes. So this is the continuation of our discussion for gas dynamic topics. So this is a part two of our discussion on moving shock relation. In the previous sessions, we saw about Hugonoid equation, and we derived that equation, and we uh, saw some physical significance of that equation and the importance of that equation. So we concluded with the remark that so we can treat a shock wave as some kind of a thermodynamic device which compresses a gas. So the properties can be found using the Hugonoid curve, and so depending on the slope of the curve, that is actually given by the upstream conditions such as upstream density and the upstream velocity. So we can derive the properties change across the shock wave for any kind of gases. So there are we have also seen that like it's independent of velocity or the Mach number. So that makes that particular equation uh, uh, valid across different gases. So it's not exactly relying on the perfect gas assumption. It's just adiabatic process through which some gas is going to compress. So based on that, we have seen the uh, importance of Hugonoid curve, right? So in today's session, I'm going to introduce the moving shock relation. So as I said earlier, the moving shock brings the unsteadiness into the table. So we have to deal with the moving shocks in a different way. So let us look into the moving shock idea. Yeah. So when we talk about the moving shock waves, as I said earlier, so like unlike stationary shock waves, moving shock waves are categorized into unsteady flows because if you are we are already familiar with the different perspective of the fluid flows, Eulerian perspective and the Lagrangian perspective. So also we have classified the fluid flows into steady flows and unsteady flows. The difference between the steady flows and unsteady flows is such that in an unsteady flows, the properties like the point properties I am talking about, if I take any spatial location, say like I have a XYZ coordinate system. So if I take any properties or point on a system where a fluid is flowing through, so if I trace this point P, and if I measure the fluid properties such as pressure, density, temperature, or even the velocity at that point, whatever if I measure, in a steady flow system, they are invariant with respect to the time, right? So they can be changing with respect to space, but it's invariant with respect to time. That is what a steady flow means. Whereas in an unsteady flows, if I fix a coordinate system like this, and if I measure the property change or properties in a particular point in a space, so then I expect that the flow properties will change with respect to the time. As the time progresses, the flow properties change with respect to the time. I am not talking about the different spatial locations as the fluid particle passes through. So say like the same particle can be moved to a different location. I'm not talking about whether the property changed between these two points in a space. I'm particularly talking about the point of interest, that is this point P, where the properties are changing with respect to the time. If I measure at T1 and at T2, so they might be different. So they are different. So that's what the unsteady process are categorized as, right? So moving shock wave is a unsteady process because what happens, like see, you think of a system in a Lagrangian perspective or the Eulerian perspective, right? So it's the same analogy I can bring in here. So say like you are on a football field, and so you are observing as an audience. So like you are sitting in an audience seat and you are observing the play. So now what happens if the player over here or goalkeeper, say he kicks the ball on the field and you observe the ball as it passes through. So say like he is kicking it with a constant velocity and there is no other acceleration force. The moment when it leaves the um, foot of a goalkeeper, it attains the constant velocity and it travels with the constant velocity. And if you want to study the flow field around the ball, so you can approach in two different perspectives. One as a stationary observer who is sitting in an stadium and observing the play. So what he thinks is like, let us simplify the problem and make that so whatever the velocity at which the ball is traveling, let me keep that in a different way. So let me keep this ball in an internal setup where I'm keeping the ball fixed and allowing the flow to come in an same velocity as it is moving in the football field. So now what you are doing essentially, you are fixing the ball and allowing the fluid to flow at the same velocity at which the ball is actually going. So the relative motion between the ball and the fluid surrounding it is going to be the same. But while doing so, what you have done is you simplified your problem from an unsteady flow to a steady flow. Why I am saying is, think of a same system in a Lagrangian perspective. So say like a football player from the same team, the moment when the goalkeeper hits the ball, so he is also chasing the ball to the other side, right? So now what he observes, so let us say hypothetically he is also moving with the same speed of the ball. So what exactly he is observing is like he's actually tracing the ball along with that. So that means the what he is observing is kind of a Lagrangian perspective. So in this case, what happens when you fix a point in space? So like let us say football field is my Cartesian coordinate system with this corner being my origin. So x and y, and z plane is where the ball is traveling in the uh, uh, at an elevated height. So x y z coordinates. So like say that. So now if I fix any point on the football field, say at this point, if I'm fixing and I'm observing the fluid properties, say like pressure or density or the temperature, whatever, if I measure here, as the ball approaches this point, so they are going to change because the fluid flow around the ball is going to adjust because it is getting an information regarding the ball which is coming towards it. So it will adjust accordingly to uh, go over the ball. So that is why. So what happens if I measure the property change as with respect to the time? So this is always going to change because the moment when it approaches, it attains a different values, and the moment when the ball leaves, it is under the wake of that ball region, and the fluid property is going to change during that time. So overall, as the time progresses, this point will experience the different values of pressure, density, temperature, or even for sake like kinematic properties like velocity or gradient of velocities, whatever it is. So it's going to experience different values. So this is unsteady because it is changing with respect to the time. What you have done here is you are bringing it to a steady frame of reference. So now you fix the frame, and if you are measuring a point properties over here behind the ball, so it's always going to be the same because the fluid is coming at constant velocity, ball is fixed, so it's always going to be on the region where the flow properties which is not going to change with respect to time. So this is a steady state scenario, whereas this approach where what we see here is an unsteady scenario. So whatever I'm talking here is still in an incompressible limit. So this analogy can be extended to a compressible flows. Just an analogy, so we can transfer, right? So similarly, when we talk about the standing shock wave, it is kind of an all-air approach where what we see is the shock wave is sitting and the fluid is coming towards it, and there is a change in properties across the shock wave, and fluid is moving. So whatever change happens across the shock is through an adiabatic process, but the properties upstream or the downstream of the shock wave, they are going to be the same as long as the upstream conditions are not changed, right? So this is a standing shock wave. Similarly, when I have a moving shock wave, which is moving with some velocity, say Cs, the shock is moving with a velocity Cs. Then if I want to measure any properties at any point, so before it sees the shock wave and after it passes, the shock wave passes the point, the properties are going to change. So that means like it's no more a study. So it changes with respect to the time, depending on whether the shock wave is approaching towards it or the shock wave is past. So this is why I categorize this moving shock into an unsteady phenomenon, right? So getting this strong background about the moving shock wave and the classification of the flow features. So now we move on to the next features of the moving shock wave. When a shock wave moves into the stagnant medium, a gas behind the shock wave will move with the velocity called as a group motion velocity or the mass motion velocity. This is a very important feature of a moving shock wave. So these scenarios even exist in an incompressible limits, not just in the compressible limits. Whenever the heavy body which moves in the stagnant medium, say like a heavy truck which is moving on the road, or heavy submarines or the ships which moves on the sea. So what happens when they move on a stagnant medium? Immediately when they move, so behind it, whatever the masses are there, they also move along with it with some velocity. It's usually termed as a mass motion velocity. So if you recall your fluid mechanics aspects when you have derived uh, Bernoulli's equations and all. So if you go on to look at the unsteady aspect of a Bernoulli equation, there you might have found a very interesting idea called added mass effect. So especially when people analyze a flow field around the heavy bodies like submarines and all, they will take care of that added mass effect. So like it becomes less and less important when the mass of the body is less, and but when the mass of the body itself becomes much more significant, then the added mass effects also comes into picture. So it's an unsteady aspect of Bernoulli's equation. So I am not going into the details of that one, but the important point here is like similarly when a shock wave, it's a very strong compression phenomenon. So the moment when the shock wave will move in a particular direction, what it also does is it actually pulls the mass behind it. So say like here I have a very like a stagnant medium which has like no velocity component to it. So it's just stable, and so it's a stagnant. The moment when it sees a shock wave which is passing through that, so what it actually does is it induces a velocity to the particle. It actually pulls that particle with some velocity. So it also pulls the particle along with it. Note that this velocity of the particles are not same as the velocity of the shock wave. This is the velocity which is gained after the shock wave is passed. So the shock wave is pulling some particle with a different velocity. We sometimes refer with the notation UP, that is a particle velocity or the group motion velocity, right? So this is something which is new compared to the stationary shock wave what we have analyzed in the earlier session, right? So now the next one is the property change across the moving shock is often characterized using the pressure ratio rather than looking at a Mach number. Oh, this is very important. So this is why the whole exercise of deriving the Hugonot equation was taken in the last session, because when I come to a moving shock relation, the Mach number takes a less importance, whereas the pressure ratio, which actually sets the flow properties which you are going to expect, because the shock strength is defined with the pressure ratio, right? So we define the strength of the shock with respect to the pressure change across the shock wave P2 by P1, say. So in general, we define like P2 minus P1 divided by P1 as the shock strength. So for sake, like we will consider P2 by P1 as my shock strength, and this actually sets my flow properties. For a given pressure ratio, I can expect one upstream properties or a one downstream properties. So this is what going to set my property change across the shock wave, and Mach number becomes a less important over here because we are dealing with a unsteady process. Okay, now, and so this point also brings in the most of the property change across shock wave what we are going to derive in the next part of this session is usually expressed in terms of P2 by P1 rather than expressing in terms of Mach number, what we have done in our discussion of stationary shock wave. Now we are going to look into the moving shock waves as a function of pressure ratio. Okay, so going on to the next part, so governing equation for stationary shock waves are still valid for the calculation of the property change across the moving shock because these governing equations are derived relative to the shock wave itself. It's a very important step we are going to take here. It is just like transforming this Lagrangian frame to an Eulerian frame and analyzing it. So what we are going to do is, now we are going to fix the shock wave relative to the laboratory frame of reference and analyze it to derive the equation. Why? Because unsteady process is very complicated to analyze. So we have to simplify the governing physics in some way so that we can understand the physics very well. So what we are going to do is like, so relative motion between the shock wave and the fluid is what important to get the idea of the physics of the flow features. So that is why what we are going to do is like, we will fix the shock wave and we will treat that the fluid is coming at with some velocity and it passes through a shock. But while doing so, we have to take care of the relative motion of the fluid, which is attaining some velocity as soon as the shock wave passes through it. So that we will be taking care, and then we will use the same steady flow process equations what we have derived in the earlier sessions, like continuity, momentum, and the energy equation, and we are going to use that to derive the property change across the shock wave. Remember it is just a transformation we are going to do to a relative frame of reference, but still we are taking care of that relative motion of the mass behind the shock wave, and we are doing the same process what we have done in the earlier sessions. It's an important step to analyze the phenomenon, but in reality, the shock wave is moving means it's the unsteady flow physics. So that we have to keep in mind. So we are simplifying our problem to understand the physics, but we have to remember, like we have to keep in mind that so it's an unsteady phenomenon, right? So now, how can we see a moving shock wave in a laboratory? That's the question. So if you see a like real life applications, like aircraft is moving at a supersonic speeds, and it's kind of experiencing the shock wave in front of it. So as the aircraft moves, the shock is also moving along with that. So it's a moving shock kind of scenario. So similarly, like any object you take which is moving in the air and which is experiencing the shock wave, that means it's a moving shock uh, part only, because the object is moving along with that, the shock is also moving into a stagnant medium. But when we analyze in a laboratory scale, what we do is we fix the model of an object in an internal kind of setup, and we allow the flow to come at the supersonic speeds, and we analyze the property change across the shock waves and the pressure or temperature which is experienced by the object behind the shock waves and all those things, right? Similarly, we can also observe the moving shock itself in a setup like shock tubes, right? So before going to that, so like I have to explain a bit about this diagram, whatever I am showing here. This is the same idea what I have discussed in the previous slide. So it's same thing, like what the difference between the moving shock and the stationary shock. So if you see here, all my properties in a standing shock wave or the stationary shock wave in a fixed laboratory frame, so they are all just functions of the space, not the functions of time, because it's always going to fix on this location, and whatever upstream is going to have the same values all the time, and whatever the properties are there in the downstream also going to have the same values at a given point during the entire say like experimental time or whatever. So it's not going to change. It's a stationary shock. The moment when I have a normal shock which is moving with respect to my laboratory frame, I am an observer. It's just like a audience who are sitting and watching the football game. So where the shock wave is kind of a football which is moving. So it's with respect to you, it is actually moving, right? So you can see the movement of the ball. So similarly, if the shock wave is moving and you are sitting outside the tunnel and you are observing, the shock wave is moving in front of you. So it's a moving shock. So when you analyze, so this is a stationary point. So like before the shock wave comes to this point, they are all having the same properties. They are not going to change because it's a stagnant medium. The moment when the shock wave passes through, so then there is a change in properties across the shock wave, and the property at this point will going to change after the shock is passed. And also there is a mass motion velocity, so that also changes the property, right? So this is a relative frame, that is a absolute frame. This is an absolute frame of reference. This is a relative frame of reference. You are sitting outside and you are seeing as the shock wave is moving, whereas this is a absolute frame of reference where it is fixed, right? So in this case, what happens? It actually changes with respect to time also. Not only space, it also a function of time, right? So this is the same thing what we explained in the earlier slide. So now the question is like, how can we observe this moving shock wave? So that is simple. So say like there are various methods to generate the moving shock wave. So one of which is having a shock tube. What we do in the shock tubes is, so we keep a very high pressure gas or air, whatever, in one part, which is separated by a diaphragm with a low pressure region. So now what is there? There is a pressure gradient between these regions. So say region 1 and region 4. So there is a pressure gradient, and which is separated by a diaphragm, right? So this is the initial time, T is equal to 0. So this is the setup we have now. So the part which contains the high pressure is commonly called as a driver section, and the part which has a low pressure region, that is commonly known as a driven section, which are separated by a diaphragm. So if I plot the pressure versus distance in a graph, so I see the constant pressure P4 to this point, and there is a pressure change, the sudden change, and the pressure P1 on the other side, constant pressure. So now at T is equal to 0, this is the condition. Now the T is equal to T1. What I am going to do, I am going to rupture the diaphragm, allow the nature to equilibrate. So while doing so, what happens? The high pressure region and the low pressure region, we know for a reason that whenever there is a gradient, the flow can establish itself, right? So we need a gradient to drive the flow. So now we have a pressure gradient which can drive the flow. That is why the high pressure region, which is driving the flow towards the low pressure region. So that is why it is called the driver section. So now what happens? The moment when I rupture the diaphragm, what happens? The fluid at high pressure region, that the driver section, try to go in this way, right? So now the pressure difference is that high, so it can create the shock wave. The moment when you rupture the diaphragm, the pressure difference is very high, so that it can actually create the shock wave. Now, because there is a difference in the pressure between the driver section and the driven section, the shock wave will also move to make sure this pressure, the low pressure, will come to a high pressure, because it has to equilibrate. It cannot just simply flow, right? So it has to attain that value, because the pressure difference is so high. The only way you can actually achieve the pressure at P1 to P2 is through some kind of a compression mechanism, which can happen very instantly, and you don't have space to do it, because if you see the figure here, so at the same point I have a jump, right, in T is equal to 0. So it has to attain some value so quickly and instantly. So it can happen only through a shock wave mode. The moment when the shock wave originates over here, the moment when the diaphragm breaks, the shock wave is created, across which the properties will change, and it sees a lower pressure region ahead of it. So it moves in this direction, so that the low pressure region over here can attain the high pressure value. Similarly, here what happens? I have a very high pressure and it has to equilibrate. So what it does is, in the other direction or the opposite direction of the normal shock movement, we can see an expansion wave through which a pressure is gradually decreases. So in both the regions, they come to an equilibrium position, so that the nature says us this pressure and this pressure has to be balanced. So that is P3 is equal to P2. So the P3 is coming from an expansion fan which is moving in the other direction, whereas P2 is coming from the normal shock wave which is moving in the original direction or the X direction. As an observer, we can see that the shock wave is moving in this direction, and there is a pressure rise across the shock wave, and it attains the equilibrium value. So this is how my pressure distance diagram looks like after the diaphragm is broken. So this is one of the way to generate the moving shock wave and observe the property change across the shock wave and all. So in a laboratory frame or laboratory scale, right? So the shock tubes have much more significance in the research and all, because it can create a high enthalpy, high temperature gases, unlike in wind tunnel. So here you can create all this high enthalpy, high energy content through a gas wave, through a shock wave, because it's a compression wave, right? So as I said in the last session, the shock wave is compression through a shock wave is an effective mechanism. May not be an efficient mechanism, but it is an effective mechanism. So this is one of the way to get that highly compressed and high enthalpy gases to expand it through a nozzle and get the hypersonic flows and all, right? So it's a high enthalpy gas dynamic research usually goes with the help of shock tubes. Okay, so that is an application point of it, but we can generate this moving shock waves in a laboratory frame using shock tubes with the driver and driven section separated by a diaphragm. I will rupture the diaphragm and an instant it sees the high pressure parity and to equilibrate the gases to a similar pressure. So the shock wave moves towards the low pressure region and it brings the low pressure to a high pressure across the shock wave and it tries to equilibrate the system, right? Okay. So this is how we can create the moving shock. So now the question is how the property change across the shock waves can be calculated in this kind of system. So that is the question we are going to analyze now. So this is where we will come back to the relative frame of reference, right? So what we do is in a relative frame of reference, still these equations are valid, what we have used in the normal shock relations, because in a relative frame of reference, what we are doing is we are fixing the shock wave at one location and we are seeing the flow to come at some velocity, right? So across which whatever happens is what we are going to study. So, but these equations are derived, especially the momentum equation is derived in an absolute frame of reference. So you cannot just simply come and say like I will apply the Newton's law of motion in a relative frame of reference unless and until you take care of that relative motion, right? So because Newton's law of motions are derived in an inertial frame of reference. So I have to be in an absolute frame of reference to analyze whatever happens through like whatever happens in an inertial frame of reference, right? So now, so to account for that, what I do is, so now I will assign a different velocity value so that I am going to take care of that relative motion, right? So there are some notations we will be constantly using. That is, one is velocity of the gas ahead of the shock wave relative to the wave. See, in reality, there is no velocity to the gas ahead of the shock wave because shock wave is moving. But we are transforming into a relative frame of reference. So by doing so, we are fixing the shock wave and we are treating the gas is moving at some velocity u1, right? So that is velocity of the gas ahead of the shock wave, which is relative to the wave. So now we are sitting on the shock wave and seeing. So you think in this way, you are sitting on the shock wave and you are moving along with the shock wave, and whatever you see changes happening ahead of you to the behind you. So that is what you are analyzing now. So it is a relative frame of reference, right? So u2 is the velocity of the gas behind the shock wave, which is again relative to the wave. So this is my u2. Once the gas passes through the shock wave, this is what we expect, right? So this is exactly what we have done in normal shock wave the relations while deriving the stationary normal shock relation, right? So here also we are going to do the same thing. So I'm actually referring to these u1 and u2. But when I transform into a relative frame, so what is actually u1? What is actually u1? From a stationary observer point of view, if you think there is a u1 to this one and shock is having some velocity, so this is nothing but because it's a stagnant gas ahead of the shock wave, so which is at zero velocity and shock is moving at velocity w. So in a relative frame of reference, that is nothing but w minus zero. Sorry, in a absolute frame of reference, this velocity is nothing but w minus zero, at which shock is actually moving, right? So this is my velocity of the gas in a relative frame of reference, that is u1, if it is moving at this speed, right? So that is the velocity at which shock is moving that is also same as velocity at which you are expected the gas. The person who is sitting over here will experience the velocity W, which is coming towards it. Just like you are traveling in a bus or car or bike, whatever, in an automobile you are traveling. So you feel the air is coming and hitting you. So though you know as a stationary observer, you are sitting like you are standing out from the automobile and you actually see the car or the automobile which is actually moving, not the air in front of it, unless there is a gust or the breeze. So we treat in an ideal scenario, there is no movement to the air itself. So it's a stationary and automobile is moving in a air medium. So now you see, like, as a person who is sitting inside the vehicle, they feel like the air is coming and hitting you, because for you, it's a relative. If you are moving at 20 miles per hour, the air is, you feel like the air is moving at 20 miles per hour towards you, right? So sometimes you call it, like, if you ride a bike or something, you call it as a wind blast or something. If you go higher, if you throttle higher, that means like you if you accelerate high, that means like you feel like there is a lot of air which is coming and hitting you, right? It's the same scenario. So for a shock wave, if a person is sitting inside the shock wave and sees whatever happens, he sees like the gas is moving towards him, or he or she, whatever. So gas is moving towards them. So with the velocity W, at the same speed as they are actually moving towards the gas. So that's the same speed they are going to experience, right? So that is W, nothing but U1 relative to the relative to the shock wave. And what is the velocity behind the shock wave? This is interesting, because in a stationary shock relation, you just have U2, right? But the shock is moving now, and which is actually pulling the gas behind it, and which has velocity which is greater than zero. It is not zero now, whereas this is stagnant medium. You had U1 is equal to, sorry, U is equal to zero over here, but behind it, it is not the same case. Now what you see, it is, so think of an analogy. You are traveling in a car, right? And behind you, there is one more car which is chasing you, right? So now, as a person who are sitting in this car, if he sees the velocity of this car, he can't actually see, like, say this is moving at 20 miles per hour and you are moving at 30 miles per hour, right? You don't actually see this is moving at 20 miles per hour. This can be seen only by the person who is standing outside of these both cars. They can see both cars at their true speed from the absolute frame of reference. But for you, who is observing from this car and observing the car B from car A, so you see that this car is actually moving at 30 minus 20. So the relative, so 10 miles per hour, right? So it's the same case if you are seeing a car which is coming in front of you, if it is moving at 20 miles per hour, what you see is like, you actually observe like this car is coming at 30 plus 20. So you see that this car C is coming at 50 miles per hour instead of 20 miles per hour. You see it as it is coming at 50 miles per hour. It's a relative, right? For you, it's relative to your car. So this is coming slower, this is coming faster. Why? Because you are also moving at some velocity. You have to take care of that. So it's the same thing. So as you are sitting in the shock wave and you observe the mass which is behind you, so you see which has some velocity different than W. So that means U2 is now this W at which you are moving minus the velocity of the gas which is coming behind you. So that is in a relative frame, that is W minus U3. That is my U2. So this is actually the velocity behind the shock wave from an absolute frame of reference. Now we fix what is my U1 and U2 in this equation. Now we can plug in those to get the actual formulas. So whatever, right? See, now I have my governing equation written in this way. So what I do now here, I will call W, whatever W, as CS for the simplicity. CS is shock motion velocity. UP is my group motion velocity, right? So W and CS are same notation. So like different notation representing the same velocity, right? So if you want, you can derive it W also. It's fine, so entirely fine, right? So now I have my governing equation rho 1 U1. U1 is nothing but CS, which is equal to rho 2 U2. What is U2? That is CS minus UP, right? So this is my continuity equation. And what is my momentum equation? That is P1 plus rho 1 U1 square. U1 is nothing but CS, which is equal to P2 plus rho 2. What is U2? U2 is nothing but CS minus UP square, right? And what is my energy equation? So that is H1 plus U1 square by 2. So in this case, that is CS squared by 2 equal to H2 plus CS minus UP square divided by 2. So what we have done now is we simplified our problem by making it a steady frame problem. That is actually a simplification, and it's a great relief for whoever wants to do the arithmetic part of this physics. So they find it really helpful if you do this simple simplification, right? So now what we are going to do is like we are going to simplify our equations. So like call equation 1, 2, 3. So now if I want to write in terms of CS minus UP, that is nothing but CS times rho 1 by rho 2. Or my group motion velocity is nothing but CS is equal to CS minus UP times rho 2 by rho 1. Right? So what I'm doing is like I'm keeping both of these forms, right? It is going to be helpful in the further derivation. So now I am taking the continuity equation. So this is, sorry, I am taking the momentum equation. So this had P1 plus rho 1 CS square like that. But what is CS minus UP? CS minus UP is nothing but CS time rho 1 by rho 2. So I can replace that one here. P1 plus rho 1 C1 square CS square equal to P2 plus rho 2 times what is CS minus UP? That is CS times this one. So CS rho 1 by rho 2 whole square. So now if I simplify it, so 1 rho 2 and 1 rho 2 get cancelled. So this comes out to be like P2 plus rho 1 square times CS square divided by rho 2, right? Now if I write in terms of P2 minus P1, so that is what we are interested in, because we want to represent in terms of P2 by P1. So that is our end goal. So we are moving towards it. P2 minus P1, that is equal to rho 1 CS square minus rho 1 CS square divided by rho 2. So which can further simplified with rho 1 CS square is taken outside. So it's the rho 1 square. So that becomes rho 1 CS square times 1 minus rho 1 by rho 2. Right? So now if I want to write in terms of CS square, which is equal to P2 minus P1 divided by rho 1 times 1 minus rho 1 by rho 2 inverse. So, or you can take in 1 divided by this one. So, if you simplify this one, rho 2 minus rho 1 divided by rho 2, it becomes. So, it can be shown like Cs square is equal to P2 minus P1 divided by, so rho 2 minus rho 1. Let me keep like 1 divided by. So, that becomes rho 2 minus rho 1 divided by rho 2. So, this becomes like rho 2 minus rho 1 times, so the denominator goes to numerator, so that is rho 2 by rho 1. That is nothing but my Cs square. So let me call this as equation number 4. And we also have Cs is equal to Cs minus UP times rho 2 by rho 1. So if you want to write for Cs minus UP, so you can also derive and get this form. Square is going to be same as P2 minus P1 divided by rho 2 minus rho 1, but here I will get rho 1 by rho 2 instead of rho 2 by rho 1. That's that interchanges. So equation number 5. Right? Now I have different versions of these equations now. Now what I am going to do is like I am going to plug into the energy equation. So H1 plus Cs square divided by 2 is equal to H2 plus Cs minus UP divided by 2 whole square. Right? So now put the Cs and Cs minus UP square, that those forms what we have got, equation number 4 and 5. So you see that H can be written as E1 plus P1 by rho 1 plus Cs square, what we have got is half of P2 minus P1 divided by rho 2 minus rho 1 times rho 1 by rho 2 is equal to this one, but rho 2 by rho 1, whatever. So is equal to E2 plus P2 divided by rho 2 plus half of P2 minus P1 divided by rho 2 minus rho 1 times rho 1 by rho 2. For the interest of time, I am not going to do the same steps what I have done in the last class. This is the point where we have come to the same point while deriving the Huguenot equation. What you get it like, if you simplify this one and write it for E2 minus E1, you are going to see that this equation comes like P1 plus P2 divided by 2 times 1 by rho 1 minus 1 by rho 2 or mu 1 minus mu 2. So you are actually going to get the Huguenot equation. It is not a surprise. It's an expected result, right? So because it relates all the thermodynamic variables. So we are taking the help of all the governing equation and we are arriving at the same idea. And so we are expected. So this is how it has to look like. And we are going to get the Huguenot equation. So let me call it as equation number 5 or 6, whatever. Right? But the next step is I am going to derive it for calorically perfect gases. So till this point, I am not assumed any type of gas, right? So now I am assuming, let us say we are analyzing it for calorically perfect gas, because now we are going to see more of the physics aspect of the problem at hand. So that is why I am simplifying further by assuming it's calorically perfect gas, right? So now if I use that one, I can use CVT kind of idea for T. So that becomes T2 minus T1 is equal to, again, so the specific volume can be written in terms of pressure and temperature using the equation of state. P is equal to rho RT or P nu is equal to RT kind of idea. Nu can be written as RT by P. So this is P1 plus P2 by 2 times RT1 divided by T1 minus RT2 divided by T2. Given that R is constant, so CV is nothing but R divided by gamma minus 1. R divided by gamma minus 1 times T2 minus T1 is equal to P1 plus P2 divided by 2 into R times T1 by P1 minus T2 by P2. So R and R can be cancelled from each side. Also, if I take T1 common, so I can write in terms of T2 by T1. If I take T1 common divided by gamma minus 1, that is T2 by T1 minus 1, which is equal to T1 plus T2 divided by 2. If I take again T1 common here, so what I get is like 1 by P1 minus T2 by T1 times 1 by P2. So T1 and T1 can be cancelled from each side. So what I'm trying to do is like I'm trying to write in terms of T2 by T1. So now if I take gamma minus 1 other side, so this equation looks like T2 by T1 is equal to gamma minus 1 by 2 times P1 plus P2 times, so take the LCM, T2 minus T2 by T1 times P1 whole divided by P1 P2 and here is minus 1 which comes to this side, so it becomes plus 1. So now what I have is T2 by T1 is equal to 1 plus gamma minus 1 by 2 times if I take P1 P2 this side, so that becomes P1 divided by P1 P2, that is 1 by P2 plus 1 by P1 times P2 minus T2 by T1 times P1, right? And again I can take this inside. So like for the interest of time, I am not going to show all the algebraic steps involved over here, but this will actually going to simplify. Like what is our goal is to represent in terms of P2 by P1. For that, what I can do, go on to do one more step. Plus gamma minus 1 by 2. So let me keep like this only. P1 plus P2 divided by P2 P1. So if I take this inside, so what happens? Gamma minus 1 by 2 times for the first term. So it becomes P1 plus P2 divided by P1 P2 times P2 minus gamma minus 1 by 2 times P1 plus P2 divided by P1 P2 times T2 by T1 times P1. So now what happened? So here P2 P2 get cancelled, here P1 P1 get cancelled. So now take this T2 by T1 term other side. So now it becomes, if I take T2 by T1 common, so it becomes like 1 plus gamma minus 1 by 2 times P1 plus P2 divided by P2 equal to 1 plus gamma minus 1 by 2 times P1 plus P2 divided by P1. Right. So now take to other side, keeping T2 by T1 in the left hand side. So this becomes 1 plus gamma minus 1 by 2 times. So this one I can write P1 by P1, that is 1 plus P2 by P1. So that is nothing but 1 plus P2 by P1 divided by, in the denominator, 1 plus gamma minus 1 by 2 times, again P1 by P2 plus P2 by P2 is 1. So that is 1 plus P1 by P2. Again, you can go on to simplify this. So go on to simplify this. T2 by T1 is equal to, what I had is like 1 plus gamma minus 1 by 2 times this one. So if I take the LCM, so that becomes 2 plus gamma minus 1, and again I am taking inside. So that is 1 plus P2 by P1, that is gamma minus 1 times P2 by P1 divided by, again here 2 plus gamma minus 1 plus gamma minus 1 times P1 by P2. So if I simplify this one, what happens? That is 2 plus gamma minus 1, that is gamma plus 1, right? So it becomes like gamma plus 1 plus gamma minus 1 times P2 by P1 divided by gamma plus 1 plus gamma minus 1 times P1 by P2. So now what I am doing is like, I am taking that gamma minus 1 outside from both the equations. So that becomes like gamma plus 1 divided by gamma minus 1 plus P2 by P1 divided by, again, gamma plus 1 divided by gamma minus 1 plus P1 by P2. Right? So now I can take P2 by P1 common from both the equations, both the terms. So that becomes T2 by T1 is equal to, if I take P2 by P1 common here, becomes 1 plus gamma plus 1 divided by gamma minus 1 whole divided by, again, if I take P2 by P1 common here, so that becomes gamma plus 1 divided by gamma minus 1 times P2 by P1 plus 1. Sorry. What we have here is like, here I had P1 by P2. P2 by P1. Okay, so sorry, here I am taking P1 by P2 outside. So if I take P1 by P2, this becomes P2 by P1 plus this is 1, right? So I'm not taking P2 by P1 over here. So I'm just keeping like that. P2 by P1 plus gamma plus 1. So now what is happening implies the temperature change across the shock wave is nothing but gamma plus 1 divided by gamma minus 1 plus P2 by P1 divided by 1 plus gamma plus 1 divided by gamma minus 1 times P2 by P1 whole multiplied with P2 by P1. So now you see here, we express the temperature change across the shock waves, the static temperature change across the shock wave as a function of P2 by P1. That was the goal we started off, right? So I told you in the beginning, so all property change across the shock wave are now treated as a function of pressure ratio instead of Mach number. Similarly, for density change across the shock wave, what I can do is like I can use the equation of state relation. Rho2 by rho1 can be written in terms of this we have done numerous times, T2 by T1 times T1 by T2, right? So now I know T1 by T2 as a function of P2 by P1. You substitute over here, so you are going to get, so here already one P2 by P1 is there, and in T2 by T1 also one P2 by P1 is there. So it becomes like P2 by P1 multiplying. So it is the inverse of that one. T1 by T2 is nothing but 1 by T2 by T1. So if I use that one, it becomes like 1 divided by P2 by P1 times. So numerator and denominator exchange over here. So that becomes like 1 plus gamma plus 1 divided by gamma minus 1 times P2 by P1 divided by gamma plus 1 divided by gamma minus 1 plus P2 by P1. So now this P2 by P1 and this P2 by P1 cancel. So my rho2 by rho1 now looks like 1 plus gamma plus 1 divided by gamma minus 1 times P2 by P1 divided by gamma plus 1 divided by gamma minus 1 plus P2 by P1. This is my density change across the shock wave. It's a function of pressure ratio, right? But why this is important? Like all we have done is like representing different property change across the shock wave as a function of P2 by P1. But main motivation is like we have to calculate at what speed the, like as I said earlier, the one way of creating this moving shock wave is by having a diaphragm which separates the driver section and driven section. So it's a shock tube, right? In that scenario, what we actually know is the pressure ratio, because we know at what pressure my gases are filled in the driver section and what pressure my gases are there in the driven section. So that is what we know in the initial. If I rupture the diaphragm, then my goal is to calculate at what velocity the shock wave moves within the shock tube and what property change it actually brings into the table. So like if I have P4 and P1 and if I rupture the diaphragm, what is P2 by P1 I am going to expect, and what is the velocity at which the shock wave moves, W. So that is bit important to us. So to calculate that one, so what we are going to do is we are going to take a help of this Mach number relation. So that is we know P2 by P1 can be written in terms of 1 plus 2 gamma divided by gamma plus 1 times. So say the shock motion, which is at Mach number ms minus 1. So right. So this is actually the pressure change occurs if the shock is moving at this Mach number. So this taken directly from our stationary shock idea. So there I had P2 by P1 as a function of upstream Mach number. In this case, upstream is stagnant, the shock is moving. So that is why I can take the relative idea and make this equation. And indeed, like my ms, the shock motion Mach number as a function of pressure ratio. That is nothing but 1 plus, take all the other things to other side. That is gamma plus 1 divided by 2 gamma times P2 by P1 plus 1. Sorry, minus 1. Right? This is my velocity of the shock wave as a function of pressure ratio again. And but what is ms? So ms is defined as Cs divided by the speed of sound at the stagnant medium, that is A1, right? So Cs divided by A1 So that means Cs can be written in terms of ms times A1 or ms times root of gamma or T1, whatever. All which brings in is, like, if I get the value of Cs and I can calculate the Mach number, and from the Mach number I can get the pressure ratio, and if I get the pressure ratio, I will get all the property change across the shock wave. So now we are trying to get this one, and much more important point we want to calculate is, like, what is the velocity of the fluid which is coming behind the shock wave. Like, shock is pulling the shock wave, so pulling the mass behind it. So what is up? That's the next question. So we want to calculate this also. So for that, what we are going to do is, like, we are going to use the continuity equation help. But before that, so the Cs can be written in terms of A1 times ms is already known in a function of, as a function of pressure ratio gamma times. So now we can calculate Cs in this way. We know that what is the speed of sound, because before rupturing the diaphragm, we know the condition in the driven section. So that is what going to tell me what is my speed of sound in that medium. So A1 is already known parameter to us, right? Now to calculate up is nothing but Cs minus U2, right? Because we define U2 to be Cs minus up in a relative frame relative to the shock wave, or I can write up as Cs minus U2, whatever. And we already use the continuity equation rho1 U1 is equal to rho2 U2. So, or else I can write rho1 Cs is equal to rho2 Cs minus up. This is how we derived, right? So now I can write for up. So that is nothing but rho1 by rho2 times Cs is equal to Cs minus up, or up is equal to, so taking this side, take Cs common, that is 1 minus rho1 by rho2. So now we got the idea, like, how we can calculate up as a function of pressure ratio, because rho1 by rho2 I can represent in terms of pressure ratio. So if I do that, so apply what is rho2 by rho1 from this the last step what we followed. So we can get up as a function of Cs. Cs is written in terms of A1 times square root of 1 plus gamma plus 1 divided by 2 gamma times P2 by P1 minus 1 times 1 minus rho 1 divided by rho2 by rho1. So that is 1 divided by rho2 by rho1, whatever we have got in the earlier slide. So that is 1 plus gamma plus 1 divided by gamma minus 1 times P2 by P1 divided by gamma plus 1 divided by gamma minus 1 plus P2 by P. And take the LCM and simplify this step. We are going to get, again, in the interest of time, I am not going to show you the steps involved to simplify these. So I can actually write, like, if you look at this one, now I actually represented my up as a function of P2 by P1 and upstream condition. That is upstream speed of sound. That's the speed of sound in that stagnant gas, right? So you can actually get this formula by simplifying it. A1 is same, gamma plus 1 divided by 2 gamma times P2 by P1 minus 1 times So take to the numerator and take the LCM and simplify. So we get -1 times 2 divided by gamma minus 1 whole divided by 1 plus gamma plus 1 divided by gamma minus 1 times T2 by T1. So this is expression for group motion velocity. So we derived all the property changes as a function of P2 by P1 as well as for velocities Cs and for UP. So all the properties we can get if we just know the pressure change across the shock wave, like the strength of the shock wave. So we can calculate now. So this is very interesting. So here are the expressions we got by doing all derivations. So T2 by T1 as function of P2 by P1, rho 2 by rho 1 as function of P2 by P1, and P2 by P1 we can actually calculate with the help of this equation, which we derived during the standing normal shock, stationary normal shock session. And from there, we use the idea of Mach number definition and get the Cs as a function of P2 by P1 and use the continuity to get UP as the function of P2 by P1. So this is what the moving shock relations, right? So now what I am going to do is one more concept I want to emphasize over here. Unlike in stationary normal shocks, though this process is adiabatic, but the stagnation temperature is not exactly going to be remain constant in the moving shock. So let me explain it in a bit detail. So what we have done in stationary normal shock wave, we treated H naught is constant, right? Because it's a steady process. So if you recall our discussion on definition of stagnation properties, we came to one particular point. So that is dH by dt is can be written as function of dou P by dou T, right? So this is actually dependent on the unsteady process, the transient process, right? So dou P by dou T is no more a zero in this case because this is moving shocks are not a constant, steady case. So this part still exists. So for this reason, I cannot write dH by dt is equal to 0 and go on to define H naught is constant, right? So this is no more valid. So that is why in physics perspective also, we can see that the H naught is not going to be constant across the shock wave when the shock wave is moving. So this can also be seen in this way. Say like here I have T naught and T1, they are same because U is 0, the stagnant medium, right? The moment when the shock wave passes through the stagnant medium, what happens? The static temperature raises to T2. What about the stagnation temperature? Because I have UP, right? So there is some group motion velocity UP associated with that. So now this is no more a stagnant medium. This is a fluid which is moving in the medium. So that is why my stagnation temperature T02 is nothing but T2 plus this UP square divided by 2Cp. So there is a part which is associated with this. So now you see T2 is already greater than T1, right? T2 is greater than T1 because the temperature rises across the shock wave and there is a plus this velocity. UP square. So that brings in the dynamic temperature or the dynamic enthalpy part into the uh, gas. So now my T naught 2 is obviously going to be greater than T naught 1 because T naught 1 is equal to T naught 2. Sorry, T naught 1 is equal to T1 because U is 0 in this stagnant medium. So there is no dynamic temperature associated with that. Whereas a T naught 2 is nothing but T2 plus whatever the velocity the fluid is moving with. So the dynamic part is also there. And we know T2 is greater than T1 and T naught 2 is greater than T2. So T naught 2 is going to be greater than T naught 1. This argument is valid even for H naught 2, which is greater than H naught 1. Just the CP will go on to sit here. Right? So now you see, though the process is adiabatic, because it is not a steady process, that is why we see that there is a change in stagnation properties like stagnation enthalpy. There is a stagnation enthalpy rise across the moving shock wave because of the group motion velocity. It's an unsteady process. So now you see, like if our assumptions are not right, we see how much physical deviation we can get when we analyze something. So that's why I always emphasize, like whenever you define particular definition, make sure you are defining to the fullest, like you are not leaving some assumption behind, right? So this is the part I stressed during my during the derivation of stagnation properties, defining stagnation properties. Now you can see the significance of that, right? Okay, so now we will take one or two questions from previous year gauge. So a shock moving into a stationary gas can be transformed to a stationary shock by change in reference frame as shown in the figure. Which of the following is or true relating the flow properties in the two reference frames? Right? Okay, this question is very interesting. So this is multiple selection question kind of thing or something. So it is introduced after GATE 2020. So now you see, I have a moving shock system. I am transforming into a relative frame where I am making shock to stand still with the velocity, shock velocity as the fluid velocity at which the fluid is seeing the shock. Right? So it's a transformed system. Right? Now they are asking which of the following properties in the two reference frames are actually true. Let us see this very carefully. Forget about the options first. Let us see what are the things you can observe from here. If the shock is moving in this direction at Vs, right? So now, whatever the properties here I had, right? T1, T1, rho1, T01, T01, all are with respect to the stagnant medium over here. So here I have U is equal to 0. That means T01 is equal to T1, T01 is equal to T1, like, okay? Now, behind the shock wave, I know T2 is greater than T1, T2 is greater than P1, as well as rho2 is greater than rho1, plus what else we have is T02 is greater than T01, and obviously P02 is less than P01, because if you think like P02 is greater than P01, then you are physically wrong, right? So law of thermodynamics doesn't allow you to state this, right? So because there is an entropy change that is going to increase the entropy, that is due to the change in total pressure in this way. Okay. Now these are the system you can observe from here. Now, if I transform to other frame of reference by fixing the shock wave with velocity Vs, now what we are actually changing? Now the fluid is moving at some velocity Vs. So that means my T01 is no more equal to T1. Why? Because T01 can be defined as T1 plus Vs square by 2 Cp. Because we have transformed the coordinate system, accordingly we have to change the fluid properties associated with that. Similarly, P01 is not equal to P1. So they are all denoted at dash. P01 dash is not equal to P1 dash. But what are the other things we have? Now, this is again true. P2 dash is P2 dash is greater than P1 dash. That is true. T2 dash is greater than T1 dash. That is also true. But now I can say T02 dash is equal to T01 dash because it's in the moving frame stationary reference. Similarly, P02 dash is less than P01 dash because there is a entropy rise. That means stagnation property, stagnation pressure law. Now we will see. So again, rho 2 dash is greater than rho 1 dash. Now we see the options carefully. T1 dash is greater than T1. Is it true? No, because in both cases, the fluid properties, static fluid properties are same. Only the stagnation properties are going to change because we are introducing the dynamics to the fluid. But static properties are still the same. Same system we are analyzing, the same gas we are analyzing. We are just transforming the frame of reference. So the static properties are not going to change. So in this scenario, at the upstream. So T1 dash greater than T1 is not true. So I can actually omit this option, right? Now, this option, T1 dash is equal to T1 true. T2 dash is less than T01. Very interesting. So we know T2 dash is greater than T1 dash, and we also know T1 dash is equal to T1, and we also know that T02 is greater than T01. So you see, T02 is greater than T01. So now if you compare, is T02 is greater than T01 and T01 is nothing but T1. So if T2 dash is greater than T1, that means T1 is also equal to T01. So that means there is no way that T2 dash is less than T01. Right? Because it has to be greater than T01. So this option is also not correct because this is not correct. Now the option C. I have T1 dash which is less than T1. Not correct. That because we know T1 dash and T1 are same. So this is not correct. The option 4 says T1 dash is equal to T1. So now we omitted 3 options. The option 4 has to be correct. So the P2 is greater than P01. P2 is greater than P01 is true, right? Because we know P2 is greater than P1 and P01 is same as P1. So P2 is greater than P01. That is correct. So now this one is P0 P01 dash is greater than P01. That is also correct because P01 is equal to P1 and P01 dash is greater than P1 dash. So obviously this is correct. This is also correct, right? T01 dash is greater than T01 because T01 dash is having a value greater than T1 dash and T1 dash equal to T1, which is also equal to T01. So this is also correct. So in this case, option D is correct. It's a very interesting question, which involves which actually tests your understanding of this moving shock idea. Right? Okay. Now we will move on to the next question. That is a strong normal shock wave with a pressure ratio of 29 across it is traveling into a stationary air with the gamma is 1.4. They are treating it to be perfect gas at T is equal to 280 Kelvin in a straight duct. It's kind of a very similar problem like the shock tube what we have discussed. The magnitude of the velocity of the air induced behind the shock wave is. Okay. All they are asking you to calculate QP is what? If the shock is moving in the straight duct with the stationary air at T01 is equal to T1 is equal to 280 Kelvin, with the pressure ratio across the shock is measured to be 29, that is P2 by P1. Then what is the velocity over here? So now you see, like I already know I can represent my V in terms of P2 by P1, and also given that the upstream stagnation or static property, whatever, to calculate area, speed of sound, gamma RT. So if I know these two, I can actually calculate V, right? So now I will going to show you the two approach. One is a straightforward, applying the formula. So we already obtained the formula for UP as a function of this one, right? A1 times root of 1 plus gamma plus 1 divided by 2 gamma times P2 by P1 minus 1 times P2 by P1 minus 1 times 2 by gamma minus 1 divided by 1 plus gamma plus 1 divided by gamma minus 1 times P2 by P1. So now I already know what is P2 by P1, that is 29, and what is gamma, that is 1.4, and A1 can be calculated with root of gamma RT1 because T1 is given in the problem. So if I use this formula and get the answer, so I will get UP to be equal to 1342 meter per second. So this is one way, but obviously this is very hard to remember these kind of formulas. Like even if you miss one plus or minus sign in this expression, so you are going to get a different answer which is not correct. For these kind of problems, I always suggest you to approach fundamentally. So like take a one step back and do it from the scratch. So there you are going to make no mistakes. Because I know my continuity and momentum and the energy equation can still be valid if I transform the system, right? So I can still calculate this one, P2 by P1 is equal to 1 plus gamma plus 1 divided by, 2 gamma divided by gamma plus 1 times ms square minus 1. So from here I can actually calculate ms. So that is, because P2 by P1 I know that is 29 minus 1 28, and multiplying that one, so ms can be calculated with the help of P2 by P1 and gamma, which is given in the problem. So we get ms is equal to, I am not going to show you the steps. Ms is going to be 5. Calculate. Okay. So now I also have the continuity equation with me. That is rho1 u1 is equal to rho2 u2, or rho1 times the shock motion velocity w equal to rho2 times shock motion velocity minus the group motion velocity. In this problem, they are denoting it as V. That is what they are asking you to calculate. So I am going to use the same notation, W minus V. Right? So, or I can also write it is as rho2 by rho1 is equal to W divided by W minus V. Okay. So now if I get rho2 by rho1, that is also given in the problem, the expression for rho2 by rho1. I can use this. Gamma plus 1 m square divided by gamma minus 1 m square plus 2. So that is rho2 by rho1 is nothing but gamma plus 1 times m square divided by gamma minus 1 plus m square, something like it, right? Gamma minus 1 m square plus 2. Sorry. M square plus 2. So if I use that one, I can calculate rho2 by rho1 because my m is nothing but 5. I already calculated. So I will get rho 2 by rho 1 is also equal to 5. Now I know what is rho 2 by rho 1, and I know my continuity equation gives me this expression for the moving shock. So rho 2 by rho 1 is 5 times W minus V is equal to W. Or V is equal to, so you take that side, so that becomes 4 by times W, right? So now if I know what is W, I can calculate V. So how can we calculate W? So W is again can be calculated using MS is nothing but W divided by A1. To calculate this one, so I know what is A1 with the help of T1, and what is MS I have already calculated. So W is nothing but MS times A1. So that is nothing but 5 times root of 1.4 into 287 into 280 Kelvin. So I will get it to be like 1677 meter per second. So if I substitute back over here, I will get V is equal to 4 by 5 times 1677. So that gives me V is equal to 1341.6. So they are asked you to round off, I guess, round to a nearest integer. So I can round off to P is equal to 1342 meter per second. See, so we are dealing it from the scratch and we are able to get the same answer, right? So this is a much more robust approach, so that like you are going to make a less mistake over here, because if you are clear with the concept, so you can always approach this kind of problem, right? Okay. So this concludes my discussion on moving shock relations. So if you have any further queries, you can contact us in iitiansgateclasses. So thank you for your attention.